I'm here to talk you about networking in the clouds. And while all the other talks in this session were about private clouds, let me make it extremely clear that this is about public clouds. Now, like it or not, clouds are here and they're gaining popularity. We can talk about baseline usage, but they are really great for prototyping and urgent compute activities. And the funding agencies are taking notice. NSF has founded several awards, starting with the ECAS ones. SDSC Expanse has cloud explicitly in the proposal text. There is Cloud Bank, and I personally am part of an EAGER award that was funded just to do cloud exploration. Now, when you go to the cloud, you want to know what you're paying for. And the compute part, it's pretty well understood. All the client providers have excellent documentation about the various cloud instances, what CPU or GPU you get, memory and stuff like that. But the networking, it's not really that well documented. You have some information about what you can expect locally, the pricing, but not really what happens once you leave the node. So this is why this work. We wanted to understand what can you expect when you go to the cloud. Now let's start to see what happens inside the cloud, and in particular when you stay inside a single region. And I will use storage as a proxy. Why storage? Well, we only storage for starters, and all cloud providers operate a large pool of distributed storage, and when you go to the storage, you will go over the network. And my tests show that the storage really doesn't seem to be a bottleneck. And especially when you go over wide area networks, you see that the networking really becomes the limiting point. So I started by looking how much can I get inside a single region against the storage, and then compare that to when I go over the wide area network. And on top of that, I think a lot of people are actually interested in cloud storage. While I'm not claiming this is a very detailed study about cloud storage, it does give you some idea of what you can expect there. So what do my tests show? They show that as long as you stay in a single region, getting over 1 terabits per second from the instances to their cloud storage, it's easy. I got above 1.5 for all the cloud providers, and I probably could have gone more. I just was not really interested in going way more. About 1 terabit per second is where I said, okay, this is good enough, I'm happy with it. And then, as I said, I use that as a baseline to see how much can I get going over the wider networks between regions. And I can say I was impressed there too. Several gigabits per second are the norm across all major regions, and for the less traveled ones, usually you get at least 100 gigabits per second. Although there were a few that were a little lower. I have to say Google was really impressive. All the links I have tested were above 1 terabits per second. So really, really good. So networking in the cloud actually is quite impressive. Now, I have a lot of details in the following slides, but less than 15 minutes for this session. So I will leave the details to the reader. The slides are available offline. And we'll just stick to the main talking points. Let me just point out one thing, that all cloud networking toward their storage is based on HTTP or HTTPS. And I know there was a lot of talk in this community about moving from, let's call them proprietary protocols to the standard HTTP protocols. So you can see high speeds are possible with HTTP. There is no reason to not use it. So here are the various numbers. As I said, you can look them up. I don't have the time during this talk. So now let's see what happens when you leave the cloud and go toward the scientific networks. And starting with getting the data out of the cloud. Why? Well, it may be obvious, but you pretty all much know that virtually nobody spends 100% of their time in the cloud. You may want to generate the data in the cloud, but then you want to get it out so you can analyze it, and that often is done on-prem, or you park the data in the cloud because they have really good cloud storage, and then get it out on a needed basis for whatever reasons. In both cases, understanding how long it will take to get the data out is very important. As I showed, in cloud storage bandwidth is not to worry. So the limit is really in the interface between the cloud and your network provider. What did I see when I test this? At least in the US, we get pretty good numbers. We get about 30 gigabits per second if you stay in the same region, and 20 gigabits per second coast to coast is pretty normal. Assuming, of course, that your own infrastructure can handle this. I had a node with 100 gigabit NIC and 100 gigabit per second out of the network of the out of the campus too, so that was not a problem. Just be careful that you actually have everything set up well. One of the tests was using Internet 2 DTNs, which are supposed to be high-end, but when I first ran the tests, I couldn't exceed 2 gigabit per second, which was quite unexpected. So I talked to their network teams, and after looking a little bit around, they found out that yes, there actually was a misconfiguration of that node, and after they fixed that, we got the expected numbers. And here you have the two slides after and before, and I will not go too much into details, but the results can be obtained. Just be careful that everything is properly set up. Now, the other part of the equation is data going into the cloud. Maybe because you want to do analytics in the cloud and you need the data in. You can either do it asynchronously or streaming, but in either case, the data has to get in. For this test, I used the OG supported stash cache, which is basically X through D, which HTTP as a transfer protocol. As you see, same protocol as going to a cloud storage. So the results are comparable in terms of protocol, at least. And the numbers are also comparable. You get pretty much the same results you got for getting data out of the cloud, between 20 and 40 gigabits per second. Although I did peak at 60 gigabits per second getting to UCSD, which was a nice surprise. I also have some numbers in the following slides regarding performance going to a local cache or a remote cache, because we have only a certain amount of on-prem resources that you can get data from and then into the cloud. And pretty much all the combination were above 10 gigabits per second, which was good. Just a couple of them were in the 6 gigabits per second range, and you can see all the details in the next few slides. The other interesting thing was that the UCSD node, which is on the Scenic network, seems to be extremely well connected to the cloud, and it was the fastest one to serve data to any region in all the clouds, even faster than the local ones that we had in a few regions, which was a nice surprise and means that we could do better in those other regions. So as said, we have all the details here. Not enough time to go over them. Please look at the slides at your own pace. The other aspect that a lot of people are interested in is using GridFTP. Why GridFTP? Well, traditionally that was the workhorse of file transfers in the scientific networks, and it's used for bulk file transfers between DTNs and also for moving data in and out of the worker nodes. In this case, I mostly been focusing on DTN to DTN use case, which means single node to single node. And I have all the numbers in the next few slides as before, but the salient result points are that if you deploy GridFTP in the cloud and then stay just in the cloud, you get pretty much the same results as if you were staying on-prem, which is about 30 gigabits per second. Once you get out of the clouds, if you stay to a region close to where you are, 10 gigabits per second is pretty easy to achieve. But once you go over large distances, you cannot really go that high anymore. Getting 8 gigabits per second was a struggle, and most of the tests are in the 5 gigabits per second range, which was a little bit disappointing, but not too shabby. So as I said, here are all the numbers. And finally, a couple of words about cloud networking costs. Why? Well, because you do pay for networking when you're in the cloud. And a lot of people get surprised by that, because when you use your scientific networks, you don't pay for it. Well, at least not you, the final user. Somebody has to pay it, but not you. Instead, when you go to the cloud, it's typically the final user that gets to pay for the networking itself. The good thing about this is that all cloud providers have basically the same model. All the incoming network traffic is free, so you don't have to worry about it. If you stay within the same zone in the cloud, networking is free too, so no worry there. However, when you get the data out of the cloud, you have to pay for it. And by you, I mean whoever is hosting the data in the cloud. So be careful. If you make some of your datasets public, you will pay the networking for anyone who accesses it. Also, be aware that moving data between cloud regions can be expensive too. Less expensive than getting out of the cloud, but still not free. How expensive? Well, I have more details in the next few slides as usual, but the ballpark number is about $70 per terabit egress from the cloud, and about $20 per terabyte of data moved between cloud regions. So if you're moving a few gigabytes in total, it's a no-brainer. It will be really, really cheap. Terabyte, you may notice it, but it's still acceptable. Start to move petabytes and it gets really expensive. Now, know that most cloud providers have agreements with most research institutions to waive network costs of up to 15% of the total bill. So if you actually compute a lot in the cloud, the networking may be free. Now, how much is 50%? I'll use AWS spot pricing as a reference. Azure and Google are not that far off. And in using that as a reference point, you can transfer for free out of the cloud for every 12 hours of a single core CPU, or 1 hour of an 18-core 36-thread CPU instance, or if you are into the GPUs, 30 minutes of V100 will give you enough credit to transfer out 1 gigabyte of files. So it's maybe actually cheap if you compute a lot. So more details as usual, and that's all I have really. So in conclusion, cloud computing, and with this I mean public cloud computing, it's starting to be an important part of many science domains. And while computing is normally well understood, networking has traditionally not been, and this is what I aim to change with this talk, at least a snapshot in time. We show in this talk that the cloud providers have invested heavily in networking, so the in-cloud networking is not an issue at all, so you don't have to worry about it. It's really when you have to get in and out of the cloud, make sure that whoever your cloud science network provider is has good peering with the clouds. And finally, be aware that you will have to pay for egress. So if you transfer a lot, it may be expensive, but if you have some data associated with computing, it may not be a big deal thanks to the 15% waivers that cloud providers do for research institutions. And just some acknowledgements, and this is all, and I'm open for questions.